Hello, I'm JTC 495. I'm just recording homework 1 and also additional feature for tall building, the analysis and design. As you know that homework 1 is just hand calculation and finite element software, which is ETABS exercise and introduction, right? The example homework 1 is 100 feet tall and 10 feet wide and 12-inch long the wall sections. Cantilever, we have a 100 kips lateral force at the top. Then here the 4,000 concrete, and we calculate the total deflection based upon this the lateral loads. And also I think we practice the formula hand calculation, and we run the homework 1 ETABS model to see how hand calculation based upon theory, beam theory, and finite element software, the output, how they are compatible. So we confirm that they are pretty much similar, right? So that is the one thing that would complete. But second one here, I try to introduce you the P delta effect. Since building is getting taller and taller, slender, obviously the building when is experiencing lateral load, which is our the homework 1, we have a horizontal force, which is likely the wind load and seismic, and pushing the building and deflect horizontally. So when you see in the diagram, the building's gonna sway horizontally, but you have a data load, right? Building each floor and self-head is pushing down, so it generates second order effect, which we call P delta effect. So when building is deflect, I think we need to consider this also second order effect, P delta effect, for our all the vertical element design. So P delta effect is been explained as a nonlinear phenomenon, which is geometry nonlinearities occur when actual load acts on a structural member's deformed configuration. So we need to consider this and at the deformed configuration. So again, this is very relatively significant in cylinder member. So tall building design, we should consider this P delta effect. There is a large P delta and small P delta. You can see that. And the structural analysis, like ETABS, we consider large P delta throughout this exercise, but small P delta is something I think member level. When you design the column, you probably aware that depends on your member level slenderness effect, you need to consider some small P delta by playing with amplification factor, which means it generates additional moment on the member level. So ETABS model here I'm showing, I think you're familiar with. You run this model before and you check the all deflection and shear force diagram and the bending moment diagram. Just for recap, I will show you we have dead load and wind load. But wind load, we have 100 kips at the top. The building, you can see there's a 100 feet tall, right? So I'm gonna show you here how to define there is a P delta options. The default usually the P delta effect is turned off. So when you run the model, you remember that your hand calculation for shear bending moment is a very piece of cake calculation. The shear force should be 100 kips. Bending moment should be P times the length, right? So here the shear force is all 100 kips, and bending moment is at the bottom 100 kips times 100 feet, so 10,000 kip foot, right? So easy. We already calculate the deflection, and you could check it later. All right, now what I'm gonna do, I'm gonna show you turn up. Because I tried to make this one effect a little bit visible, so I make all this self-fade overall building elements self-fade amplified by 100 times. So I'm running with this 100 times self-fade gravity effect with this P delta analysis. So first one is non-iterative method. I'm gonna run. I'm gonna show you the member forces first. This is non-iterative method. So now shear force diagram without P delta, we had a 100 kips, but now we have a 107, right? And 107, 107 kips. Now bending moment diagram here, I see 10,456, right? 10,000. So basically moment was increased by almost 450 kip foot, right? So basically you could see that. You could also check the deflection. I think it might be the deflection increase slightly. All right, so this is what you see. P delta effect is second order effect under the deformed configuration based upon your horizontal forces. Your gravity effect will generate additional moment and shear. But non-iteration method is also include some they using some virtual the lateral equivalent lateral force based upon your mass distribution over the height. So you see that some shear force increase as well. Now I'm gonna switch to the P delta iterative method. Again, 10 times more dead weight effect. Did I say 100 before? I used 10 times the self-fade. For this case, is iterative method. So I'm gonna just turn on the shear force diagram again. But this case, iterative method doesn't increase the shear forces. Instead, they increase the bending moment diagram a little bit more. So bending moment value at the base slightly bigger than just non-iterative method. Here I see the 10,400, almost 60, right? So I look at this, and in a kind of copy all the output. Without P delta, we have a shear force of 100 kips, moment 10,000 kip foot, right? With P delta, but non-iterative method, I have 107 kips shear, but the bending moment is 10,456, so 456 increase. But iterative method, shear force is still remains same, 100, and bending moment has been increased 10,460. So because this example maybe not relatively tall enough, slender enough, so you don't see much this P delta effect increase. But when building is much taller and heavily loaded, I think this increasing the P delta increase effect. P delta effect is getting higher. Typically, I remember that P delta effect, I think typically for high-rise building, 60-story building, depends on your building's slenderness. I think it's about 10 to 15% is actually increase. So why don't you run then your model with the P delta one or the other, non-iterative method, iterative method, and check your total building story and overturning moment, and check the deflection based upon the wind load. So that this is kind of good example, and tall building structural engineer should consider during their building design. Okay.